So, hello everyone. Welcome back to a new EDT community talk. First of all, Happy New Year. Our today's speakers is Pieter Pauwels. Next month, on 9th of February, we'll have Haris Isakovic. And in March, it will remain to be announced. So, our today's talk, it will be about digital twinning in the architecture, engineering, and construction sector. Pieter is Associate Professor at the Department of Built Environment at TU Eindhoven. He's involved in a number of industry-oriented research projects on topics affiliated to AI in construction, design thinking, building information modeling, linked data in architecture and construction, or semantic web technologies. He is also board member of Eindhoven AI Systems Institute and the European Council for Computing Construction, and associate editor for automation in the construction. His recent research projects focus on the web-based building information handling. And I would like to thank you very much for willing to give a talk for us today, and the floor is yours.
Okay, thank you very much for the introduction. My screen is already shared, I assume. Yeah, so
Yes.
Let's go ahead. So as you said, my name is Pieter Pauwels. I'm doing this seminar from Eindhoven, from in the Netherlands, a bit less cold compared to last week, and I will be talking about digital twinning in the AEC sector, and I will mostly cover in about half an hour to 40 minutes what we do with web-based virtual building models of our built infrastructure. It will be mostly on buildings, and the idea is to just show a few things on research that's ongoing in terms of digital twinning in our sector. I'm happy to see a few familiar faces and familiar names in the audience. That's really nice. Thank you for joining. Also for everybody else, I'm really happy to be able to share a few things. For some of you, the slides will be a bit more familiar, or at least the topics will be familiar. And for everybody else, please welcome to join. There's questions in the end. I'm happy to answer them. So my background, so where do I start from? This is something I typically share as a general context. So my background is in construction sector and architectural engineering, which you can see mostly on the left, where you have these building information modeling tools. So for those who are not familiar with it, nowadays we are less occupied with AutoCAD 2D plans, but we are modeling our buildings in 3 dimensions, including all of the information. So as soon as you're building a hospital or a facility or a very large buildings, most contractors and engineering companies make a full 3D model, a single 3D model, from which you can then derive a number of 2D plans. You can see them on the slides on the left. And every of the building elements comes with certain semantics, some information included, so that we can organize the construction site and that we know that we're building. So basically, this is virtual prototyping. The idea is to make fewer errors or mistakes on the construction site and to reduce communication errors. On the right side, you can see a graph of the same thing. So on the right side, you can see a graph database, which is actually an export from what you see on the left. So what we are looking into is to make sure that we can use the information that would have available in a BIM model, and you can use the information also on the web for all sorts of reasoning and organization of information. So one of the ambitions that I have since quite a long time, it's on the title of the slide, is to actually move our building data from these 3D modeling environments into the web so that we can interact more directly with it. Similar to how we are able to log into our flight, log into our building, log into our hotel, book ourselves an Uber. I would really like to be able to log into our building and actually know what the information is about this building. So that's why I'm trying to do this. And then during the presentation, I will cover some of the information that you can see here on the slide, which are ongoing research projects. And they are they are situated around 3 topics, namely smart buildings, robotic navigation, and circularity. Why is that? If I have to explain what we do in terms of information systems research, we very seldom make an IT system or a data system just for the sake of making it. We want to make it for a purpose, and these are the purposes. So we want to make smart buildings with a decent background infrastructure. We want to enable circular reuse of materials and resources with a similar backend. And we also want to enable, for example, indoor robotic navigation, also using the same backend data set. So I'll guide you through this. For this talk, I have 2 parts, 2 big ones. The first one is on buildings and semantics and gives a bit of background on building information modeling and link building data, and that is actually related to the topic of digital twinning. So what does digital twinning look like in our building sector? And that's and then the second part will be digital twinning in action, and there we'll cover those 3 example cases to show what we can maybe do with it as soon as we have ourselves a data-oriented digital twin. So, okay, buildings and semantics. This is, by the way, this is a book that we wrote. So many of the items that I will talk about on buildings and semantics are written down here in this book on data models and web technologies for the built environment. That's a 2022 book, 2021. This is from the period that we were confronted with Corona. So that was a perfect time to write a book. So some of the topics are also in this book. So what do we do when we are modeling our buildings and our built infrastructure? In most lectures and classes, I try to explain that we are doing a form of object-oriented modeling. It's even very straightforward because we can really touch every of our elements in a building. So we have our tables, we have lighting systems, we have walls, we have windows, we have doors. We really have plenty of objects. And when we want to model our building, this one here, it's one of our buildings on the campus. We are making a small information system that represents information about all of those objects, how they are related to each other, and so forth. And we make some kind of universe of discourse that says, this is what we have, this is how we're going to model it. It's not the real world, but it's a model of it. And in that environment, we have objects available which are physical or conceptual things. All of them have properties, which are kind of key value pairs, attributes and values often. And we have links between them, which are connections between those objects or relationships. And every object has a unique identity. These are very basic properties that I try to explain to architects, engineers in our education. But for any computer scientist, they should be rather default. So this is how we are modeling the information of our built environment. And we have several schemas for that. So all of our software, or many of our software, have object-oriented models. And this is an example, a UML class diagram in Eindhoven software that shows the biggest foundational schema that we have for our construction sector, which is the industry foundation classes. So these are the foundational classes of our construction industry, which comprises of approximately 1,000 classes, many properties, relationships, and so forth. So we have a full schema model for our built environment, which allows us to communicate about our built environment. And the idea is that the different software environments that we have are able to export their information following this YAML format, or this data model in any case. The data model, which is in a class diagram, or at least I kind of see it as in a class diagram conceptually. They have a couple of serializations. They have an express schema, an XML schema, declaration schema, an OWL schema. So those are on the schema level and therefore a bit equivalent, so they capture the same classes, relationships, and properties. And on the object side, on the instance side, we can export our building models as an IFC file or an XML file or an RDF file or a JSON file. So those should also be equivalent. We should be able to choose, I think, the data format that we're exporting our building model in. So what I'm trying to say here is that our building industry is a very structured industry. We try to organize our data. We have a very good class diagram of our industry foundational classes. And this allows us to actually work with the data across our industry to a good degree. Of course, we also need to make certain agreements. So we may have a good object model, but if we are modeling things differently, if we don't make naming conventions or modeling conventions, then things still can easily go wrong. So, for example, here you can see an example of one of our buildings where we have modeled in the red, blue, and green. You can see the boundary lines of spaces. We also have boundary lines on the walls, but we also have ones in the middle of a room, which is dividing a bigger area in multiple areas. If this is not defined that you will be modeling it this way, then it's difficult to reuse it. So in addition to the standards, you also have to define or explain what you're gonna model and how you will be modeling it. This is really important. So just working with IFC or just working with a data model does not guarantee interoperability. You have to also talk to each other and make agreements. But okay, so far so good. So what happened is that we have this very big, I'm giving you a bit of a background. What we have in our construction industry is that we have a very big set of classes, which allows us to define buildings using the same data model, the IFC Industry Foundation Classes data model. One of the goals that we have was to make this IFC schema available as an OWL ontology, so we can link it with other data sets. For example, we can link it to infrastructure data, railway, tunnel, and so forth. We can also link it to sensor data, geospatial data, and together we have one large linked open data cloud or linked data cloud of construction and architecture. So besides the real world, we could also have the linked data version of our real world, which would be interconnected across those domains. This was 2014, so that's more than 10 years ago. It's quite old. So this was the initial idea. Based on this, we have formed a community group which started standardizing the way in which we make this IFC OWL ontology and how we link to other domains. And several of you in the room know what this has been. To give you an impression, so what we have created in the past, here you can see the specification, the official specification of all of our foundational classes of the BIM industry. So you can see here on the left all the classes. Well, there are more than these. And then in the middle, you can see an XSD spec, an Express spec, and then also an OWL specification. So those were all three generated, so you could choose which language you're using. And this then allows us to exchange building data in the form that you like. That was all good. So we have produced this, and then the most common reply that I then received, or that we received after presenting it, for example, in 2017, we present this for the industry, and the most common demands that we get are these three. They want to have a more modular schema, a more extensible schema, and a schema that is a bit simpler or easier to grasp. So based on this, and I'm sorry, this is a bit of a historical story, but based on this, we decided to try to answer to these demands, to these questions, and actually make it more modular, more extensible, and simplified. And this allowed us to create, instead of one very big schema, we have created a number of smaller schemas, which always represent parts of the building sector, but not everything at once, but individual parts. So we have made, for example, this building topology ontology, product geometry, and properties ontologies. and this is 2017 plus. So here we started recreating the schema for the construction industry, a bit bottom up, REF based, and this has led to what you can see on the left. So now we can represent a building as a bot site, which has a building. It has multiple buildings potentially. Every building has multiple stories. A story can have multiple spaces. And in addition to this, we can have adjacency, containment, and also intersection. That's not on the slide, but those three are supported, those three relationships. And all of these are zones. And the second part of this bot ontology is that you can also have interfaces. So a space would be having an interface with a wall. This allows to record thermal transmittance, fire safety, and so on relationships or accessibility. This is the key structure of a building. Similar ontologies have been built for infrastructure, and these can be easily combined with other ontologies. For example, here you can see a building element ontology and a distribution element ontology. These are simple class trees, so they are just a tree with a class structure, so a taxonomy basically. So they have beams, chimneys, columns. So every element here you can be given an additional class name, which is one of these. And it allows us again to define our built environment. And may I remind you that the idea that this is very much inspired from IFC. So we try to follow a similar structure so that we are sufficiently standard. And this allows us to make a web of linked data, which is where I wanted to be. So we're able to define an instance of a door, but also of anything else, which is part of a topology. It has a product definition. We can link it to geographical data, but also sensor data, patterns potentially, and also geometry. So this allows us to kind of modularize our building sector. So that's more modular. You can extend it. You can make your own schema. And it's also simpler because everything is a bit smaller. So this is a more modular approach to this linked data. And that's where we now more or less are since a few years. So we now are able to use the commercial tools to define our built environment or buildings or AEC sector. So for example, here on the slide, you can see an example of an air handling unit, which is then connected to what it is actually monitoring and how it's related to the building. And this is now done. This example is in Haystack. That's a separate ontology that is built in the smart buildings area. So nowadays we have a whole list of ontologies available. It's really plenty. So and I think that's not bad. We can actually choose what we want to work with, and we can basically generate ourselves a cloud of linked building data. So as an engineer, you can pick a number of these ontologies, the ones that you like, or the ones you want to limit to. And based on those, you can define your, this is one of the MEP units in one of our buildings. So we can actually query it, this information about this component directly and get structured data in return. And this query infrastructure on linked data is something that is, I think, really new since the last 10 years. So I think that's something really nice to have because it makes the information behind the building model more accessible for anybody who can code with this data. Nowadays we have a whole range of schemas you can make, as in any class diagram. You can make your schema very strict, which is the more on the right side. You can make it super rich and restrictive with lots of constraints. You can make it also very loose, which you can see on the left, where you can have less domain range restrictions or cardinality restrictions, and then it becomes, if you're not careful, they become plain labels. This is not bad for more statistical approaches, but you also have the more symbolic ones on the right. So yeah, we have a whole list of schemas. I'm not going to extend much more, but this is kind of gives us a lot of opportunities to decide how we want to define our building and all of its information. So this was in a very nutshell, the kind of the story of BIM and linked data. So what I try to tell you with this is that we have a structured building sector. We have been struggling for a long time on defining all the classes and relationships that we want to store for a building. What information do we want to keep track of? And I think in the last few years, we're trying to increasingly move to the web and make sure we can connect to mainstream software tools that allow us to handle this data on the web. Right. I hope you're all with me. So if that's okay, I will now go into the second section, which is giving a few examples, and that's closer to digital twinning. So for me, the story of BIM and linked building data is a story of, to a good degree, digital twinning. Besides that, there needs to be a bi-directional communication from digital twin to the real world. So that's something I want to cover here. So I will go through these three items that gives an indication of the kind of use cases that we can support nowadays, and which I think qualify as digital twinning. And I think they're all pretty nice. So first is the smart buildings case. Smart buildings case is something that we have been looking at from the Brains for Buildings project for the last 4 years. And on the background, you see one of our university buildings. This is the Atlas building, but yeah, it has been tested also on other buildings. And now we have to go back a little bit in time. So here you can see two pictures of the basement. And there's one picture lacking of this component where there's a sticker. So if you go into those basements, you can see stickers everywhere with what, not surprisingly, identifiers. So there's identifiers on all of those components so that we can keep track of which components are in that installation. Those identifiers are unique. I mean, they're very specific to each building. They follow a certain naming convention and they align with the backend system. You can see here on the right a building management system which allows us to select spaces, select here the devices that are in there, and then to retrieve the data associated with one of those components, give or take. This is part of our smart buildings approach. So that was already there. One of the tricky things, of course, is to map that identifier with the DIT system, and then to also link it to the room booking system and so forth. This data we took and we have by the input of Lasita Kamari, we have made a brick haystack graph of this. You can see this here on the left, and this is the notation, the RDF notation, and on the right you can see the visual version. So in this graph we have all of our rooms, all of our spaces. The spaces have connections to certain sensors. So we have a presence sensor, we have a CO2 measurement sensor, and we can then indicate what those sensors are measuring and in which space they are. So you can see here the connection between space and then the individual sensor. Based on that, we have a database of our data, and then we can connect it to a web-based user interface, which allows us to select the space in which we are, which is in green. When we select it from the graph, we can then query an IoT stream that shows us the CO2 values, for example, in that room in a certain period of time. This is regular IoT data, so this is not RDF. Also in the background, the 3D data is not RDF. This is just a 3D representation. The thing that is RDF or linked data is the actual semantics, so the sensor which is in the room and what information is in the track. So based on this, the conclusion was not that we are integrating everything in the data graph. We are actually integrating it in the entire application. So we are doing a bit more system integration rather than data integration. I'm trying to re-explain. So what I consider this digital twin is that on the one hand, we have our geometry, which is 3D, components. In the middle, we have our semantics, which is what does everything mean again. We have spaces and rooms and walls. And on the right, we have our IoT streams. Those three are on the server, and we kind of combine them in a server-based digital twin. So the integration, while many would say, let's do that in the semantic graph, yeah, to a degree, it's also needing the server. So we actually need to bind the different databases together to display it. The advantage of this is that everything is in a server, and therefore we can also organize user access and security. So that's not bad. Okay, so nowadays, that's kind of a bit of a default setting that we have. And here now you can see some of the work that we do. So here we have on the top right, the digital version of our campus. So we can now select a building and then go to a story to retrieve the sensor data, which is on a different server. So here, that is not in the same graph, or it's not in the Unity, the game environment, but it's actually being retrieved from where it is stored. So this allows us to do system integration, and the goal is that we can integrate with the vendors, commercial vendors, so we can actually retrieve it from the owner of the data, so we can make decisions. Of course, and we also want to do a presence sensor. How often are our rooms being used, and what are the what's floor occupancy over time, and what can we do with this? And I'm sorry, the slide's mostly in Dutch, but you see what I mean. In the same way, so we want to track the presence of people in the buildings, but we also want to see the systems that we have in our buildings. So here we have a bit of our bidirectional communication. You can see here, by the way, the identifier. So based on how the building is operating, and based on the access, based on the planned occupation of the rooms, we can send signals to our HVAC system to actually make sure we have the right comfort, right temperature, right humidity, right lighting in time. So that's something that makes the bidirectional communication possible. And what we noticed there is that we really need to include not only the data side, but also the control. So we need to send control signals to those devices. That becomes really important. And this is something that we also do in another project with Lou1 from Bosch. So here we integrate our graph database for the building data. We have our sensor data, which is in a separate database. This is integrated. And then the question is to have a good control model on the top, which is coming from domain expert HVAC engineers. And based on the data that they retrieve from the integration layer, they can improve the model for control, so we have a better, more comfortable building. Okay, so that's the first part. So this is about smart buildings, and you can see that the idea is to move our building data on the web, so we can access it and make good decisions and actions. And for me, that's a form of a digital twin in any case. And of course, it needs a lot of work. The nice thing is that we can reuse the same data somewhere else. So because it's web-based, we don't need to exchange the file. We can just log in and if we have access. So a second case that we're looking at is this circular material reuse. Circularity is actually reusing of materials. As many of you probably know, is that our built environment is one of the most consuming industries. That's because we have so many concrete, steel, brick. We're always placing something in the world. So we have lots of resources, and to reduce the impact on our planet, we should reduce the material consumption. So we need to reuse materials. Now, wouldn't it be nice if for every one of those buildings that we have here, so these are a couple of demonstrator buildings, that we are able to list the materials that are available in that site. Because then we know, okay, this building is going to be demolished, and these materials are inside the building. I can maybe reuse that material. That's a bit the purpose of this project. This is using the following schematic setup, and I apologize for all software architects. But so every node that we have here is a bit of a building where we have the data of that specific building available. And the idea would be that we're able to query this building and ask what resources do we have available, what materials, and can we reuse this? So our data becomes much more web-based. This is the idea of logging into a building as if you would be logging into an airplane or a train or or your bank account, let's say. So you want to do the same for buildings. And this allows us to query and make a network of building data hubs. So, as an example, this is one of the houses that we have in the Netherlands, and the government maintains information about it. They know, for example, who is living there, what is the restrictions on the shape of the building, what is the energy performance of that building. Those are different databases that are available, and it would be nice if we were able at least to connect to such data. Not openly, but at least having a possibility to connect to it. Sorry, the slide comes a bit too soon. So we would have for every building, the idea would be to have a decomposition of objects, and every object has a unique resource identifier. Sorry, a uniform resource identifier. And then based on that identifier, we can track where this element has been before so that we know what characteristics it has. So every object has an authoritative URI identifier. Data follows object, so if the object moves, the data moves along. And we want to have standardized information exchange, object-centric, and with versioning included. So we can track how well the element is going through the built environment. I want to return to this. I'm not going to expand on this, but we are trying to build this using a data spaces architecture. If you want more information, I'm going to keep this for the questions. This is, in any case, a challenge, but very, very useful. So what we're now trying to do, we have here two example buildings. So all of the elements of this building, but also that building, are being given URIs, identifiers. They come from a BIM model. This building has been demolished and is being constructed elsewhere. And we want to see how well we can move also the data to the new owner, so we can track its reuse. Also, the one here on the right, those are container-like buildings. You can imagine. So those containers go back into a factories where they are being reassembled and being put back on site. So the company in this case is heavily engaged in making sure that the good elements are being reused as often as possible. Okay, that's the second case, and the third and last case for approximately 5 more minutes is on indoor robotic navigation. This again uses the same kind of data structure. So we connect to the same link data with geometry and sensor data. And we would like to navigate with this nice device here. This is the predecessor of the current robot. You can see here on the top a 2D LiDAR scanner, so 2D laser scanner, and there's lots of sensors on this platform. And this one is a mobile device that navigates through the building, which is the same building as before. Why do we want to do that? There's a couple of reasons, and I'm not going to expand on that, but usually we want the robots to take on tasks that are either pretty boring, we don't want to do them, or they're too repetitive, or they're dangerous. So those are two of the example cases. There's a case for last mile delivery, the delivery of a package and the last mile, let's say. Anyway, so we wanted to move with our robots through this building. What does a robot then need? It needs a topological map and a metric map. So it needs to know the topology of the building, which base is connected to which, and then the measurements or the sizes. So how do robots typically work? They typically use a SLAM method. So you go with the robot through the building, you map the entire building from the laser scanner, and then it knows where it can go and where it cannot go. And then it can, using this output, it can navigate autonomously. Alternative, you can manually create a world model, which looks a bit like this. So the robot knows it can navigate on this red area, but cannot hit the blue, for example. Doing that is labor intensive. This is also labor intensive. And yeah, we only know the basic environment. So the idea was to open this one here. The idea was to basically rely on the BIM model, or digital twin of our building. It's the same Atlas building. So based on that digital version of our building model, we can semi-automatically create this environment, and we can navigate directly without having to locate our robot. Super nice. I really like this project. I'm doing this. I really appreciate that we are able to do this in the same building as we can do the smart building stuff. So that's really nice. We looked into a couple of data transfer methods. Yeah, you can do it file-based, but we're actually trying to move into a server-based approach. Where you can see this LBD server, JSON data. Yeah, we're looking into what works well. In general, what does it look like? So for a building, we would have our spaces. This is a space. In the space, we know that they have adjacent elements. So we know that it's surrounded by walls and slabs and doors and so on. It contains our sensor devices. And also it has, for example, a door included. This is a door. And the door has a 3D shape. This is a 3D shape of that door. And between the door and the space is an interface. So you can see the interface is between the space and the door. And this one has a two-dimensional line representation. So I know I can go through this door on this line location. That's the ID. So based on this RDF graph in the server, we can create this the map. In principle, so for this example, we have 3D data, we have 2D data. In principle, we could extend it also with 3D data like point clouds and more, but we're working with simpler data. And that one is then used by the robot to connect from the LiDAR to the LiDAR, detects object features, which are then corners and those or other, and those can be connected to semantic objects from the BIM model. So our robot can navigate through this building. The blue line, it recognizes points, and it can recognize certain features. So for example, here there's a door modeled. So one of the things that our tests showed is that the BIM model was not correct. And that's true, it's not correct. And I said, well, it's never correct. So there's the door here, but in our map, there's a straight red line, there is no door. Also, you're navigating through the staircase, for example, and our columns are also not always exactly in place. Plus, you have furniture that was not modeled. So, based on this, what we are currently looking at is to actually update our BIM model or update our digital twin based on how the robot is navigating. So, let me just go forward here a bit. So basically, this robot is driving, and as it is driving, it is collecting those points. So you can see it will go through this staircase in a while. There's no staircase, but it's here on the map. It connects it sees the columns and those features, and based on so those features need to be matched. The wall is nicely in place. You can see the door here, which is missing. So based on these features, we can actually recognize a few things, and then maybe the added value is to update our BIM model. So this keeps on going for a while. And I will stop it here. The idea is now that we try to actually recognize elements from either point clouds or images to then update our building model, which is in a database. So it's actually quite doable. It's not like it's a separate file. So those are things that we're currently doing to recognize faces, recognize walls, recognize doors, to then make a particular updates. And then our as-built model becomes really as-built. That's where we are now. So sorry for rushing through this. I wanted to give you a big overview of BIM, linked data, and digital twins to make like a good data background, data backend, which allows us to do smart buildings, circular material use, and also this robot navigation. And in principle, they should be able to work on the same or a similar data set. So final notes, what I generally like is that that we're able to do many cases with live data, and actually it's pretty doable to represent this building information into these graphs. We have a preference. I have a preference to this RDF, not that much into labeled property graphs, but okay. But anyhow, there you can actually do it quite easily. Not everything is going into those graphs. We also have good storage solutions for geometry and sensor data. And I would really like to go to this more granular data storage and systems where we have this data with an object, and if the object moves, data goes along, and we do this on a more agile web scale. Those are the projects again, and I'm gonna thank you for your attention. I'm happy to have made it. If you want to know more, you can always contact me over this email address or online. Thank you so much.